And now we can look at the radiation dominated case. That's W equals 1/3. And again, this is a flat universe with only radiation in it. So, E dot plus 3A dot over A E plus P equals 0. P is WE, W equals 1/3. And so this becomes E dot plus 4A dot over A E equals 0. And you can do the same thing you want before. If you want, you can pull that now a factor of 1 over A to the 4, and you can multiply through. But I said I would do this slightly differently. So now let's just integrate this. Remember, E dot is just dE by dt. A dot is dA by dt. So I can rearrange the following. I can have dE by dt equals 4 dA by dt times E over A. And then I can do a bit of cancellations. The dt's here cancel, and I can get that the integral of the energy density is equal to, or the energy density divided by the energy density is equal to 4 times the integral of dA over A. Of course, that tells me there's some constants that come out, or I can put in some limits of, time t equals 0 to time today, t0. But let's just get the general state here. I'm not worrying about the integration constants. So in this case, what I get, of course, is I get that log E equals 4 log A, plus some constants. And then that tells me that E is proportional to A to the 4, just by laws of logs. So E from radiation equals some energy density that I measure today over A to the 4. And this also makes sense when you think about it, because the number density of photons, i.e. the number of photons per unit volume, is proportional to 1 over A cubed. Right, that's the same thing. If I take some gas, I double the size of the cube that it sits in, then the number density of particles goes down by a factor of 8. Right, it's exactly the same as matter, but plus the redshift effect. So photons lose energy as the universe expands. That's proportional to the scale factor, 1 over the scale factor. And so given that E photon is h nu is hc over lambda, if lambda increases with the scale factor, then the energy goes down. So this is really, again, comes out of an equation, but you can have a physical motivation for what this does. Again, I can substitute this in to the Friedmann equation. When I substitute that into the Friedmann equation, again, I go back up to the top. I've got A dot over A squared equals 8 pi g over 3c squared, and now I've got E naught over A to the 4. I multiply across by my A squared, and that tells me that A dot squared equals 8 pi g over 3c squared E naught over A squared. And if you want to, you can do the same trick again. You can guess your power law. You can therefore solve the equations. But again, I said I'd do it differently, so let's just do the direct integration. Okay, so this is dA squared by dt squared equals 8 pi g over 3c squared E naught over a squared. So let's just square root everything here. So I therefore get dA ADA here equals the square root of 8 pi g E naught over 3c squared times dt. And then if I integrate that, of course, I get that a squared dA equals all this bump here times t. Or a is proportional to t to the half. And so I can write that my evolution for a radiation dominated universe is A of t is equal to t over t0 to the half. Now, this is actually quite interesting because that means that if I plot, for example, now scale factor A of t against cosmic time t, I can have two different lines. So I can have one for things which move at relativistic speeds, radiation, and I can have another for things that move at non-relativistic speeds, which is matter. And the interesting thing, and this perhaps is less intuitive, is that the matter-dominated universe is actually slowing down less fast, or perhaps the radiation-dominated universe is slowing down faster than the matter-dominated universe. But nonetheless, I can plot them down as exactly what they are. Of course, I can also work out the Hubble parameters. Which is just a dot over a, which is equal to 2 over 3t, or 1 over 2t. I'll leave that to you to do. So you can see essentially that the expansion rate is faster for matter than it is for radiation. So there we go.